Hello everybody. So we have one last example to solve here, and this example is going to be using different coordinates. So we have been using the Cartesian coordinates the last two examples, so this is going to be using the cylindrical coordinates. So it's a good chance to get exposed to this as well. So here we have, again, you will see there are some repeated words that you will see. So here it says steady, incompressible laminar parallel flow of Newtonian fluid in an infinitely long round pipe of radius r equals d over 2. So still we can get the same assumptions from here. So it's an incompressible Newtonian fluid, and we can assume it has a constant properties. So Navier-Stokes equation is valid. It's steady flow, so the change with time is 0, and it says it's an infinitely long round pipes. So this pipe is very long. So based on this, and also based on our knowledge of the pipe flow, this is a round pipe, so we know that the round pipe is symmetrical around the center line, and based on this we know that there is no change with theta. There is no change of anything with theta. The profile is the same for the velocity profile at any angle that we see. So based on this we can assume that it's two-dimensional flow in r and z, and again these are the same two coordinates that we see here. It also says it's parallel flow, laminar parallel flow, so the flow will have only one component, which as we see is going to be in z direction. So there is no velocity in r direction or in theta direction, so ur and u theta is 0. And as we said, the pipe is infinitely long, it's symmetrical around the center line, so the theta has no effect. It's going to be purely two-dimensional flow, so any change with theta is 0. It says that the pressure gradient is constant. It's applied in z direction, so there is change of pressure with z. This is something we know, that the pressure, like we see here, from P1 is larger than P2 for P1 minus P2 P2 minus P1 over Z2 minus Z1 is dP by dz. And of course it's negative because Z increases in this direction and the pressure decreases. So delta P is negative and delta Z is positive. So this is this constant is negative. Okay. Where it says Z1 and Z2 are two arbitrary locations along the z-axis, and P1 and P2 are the pressures at these two locations. So it's just any 2 points here. We need an expression for the velocity field, and we want to find the shear force per unit area. It didn't say it here, but I think we can. Oh, it says. I'm sorry, I forgot it. It says ignore the effect of gravity. So the three gravities r, z, and theta are going to be zeros, all of them. And we know that dP by dz is constant. So these are all the assumptions that we will have. Now let's go to the boundary conditions. So we have two boundary conditions here. One of them relates to the outer or the inner walls of the pipe. The fluid is in contact with the inner walls of the pipe. So the pipe is stationary, so the velocity at r equals r capital is 0. So uz at r equals r0 is 0, and we know that at r equals 0, this is the center line, which is an axis of symmetry. So whatever is on the or above the center line is the same as below the center line. So at this axis of symmetry, duz by dr is 0 at r equals 0. So these are the two boundary conditions. I'm sorry. These are the two boundary conditions that we have. So now we can start with the equations. So we are done with the first two steps. Now we move to the third step, which is simplifying the differential equation. So of course these are the equations in cylindrical coordinates. So if you check here, we know that ur is 0, u theta is 0. So based on this, these two terms would be cancelled, and we still have the last term, which is duz by dz is 0, which means that uz is not function of z. So uz is not function of time, it's not function of theta, and now it's not function of z, so it's only function of r. Okay, uz is only function of r. So this is the conclusion that we get from this equation. Now let's see the r component. We know that ur is 0, so this u theta is 0, this and this are all zeros. dp by dr, we are not sure about this, so we will keep it now. We don't have any information whether the pressure changes with the radius, but we know that gr is 0, ur is 0, ur is 0, ur is 0, u theta is 0, and ur is 0. So dp by dr is 0, which means that the pressure is not dependent on the radius. Again, it's the pressure is not dependent on the radius. It's not dependent on theta because it's two-dimensional flow. It's not dependent of time because it's a steady flow. So the pressure is only dependent on z. Okay. So this is the conclusion we get from here. Now for the theta components, we know that u theta is 0. So all of these are zeros, and there is no change with theta. So this is 0. There is no g theta. So now we have u theta is 0, u theta is 0, u theta is 0, ur is 0, and u theta is 0. So the equation is not adding anything new to us. We're not getting any new information from this equation. Okay, so this is not helping to get anything new. We have only one equation left, which is the z component. Now the first term would be, the first term would be 0 because it's steady flow. ur is 0, u theta is 0, z is not 0, but duz by dz is 0. dp by dz is constant. We know it's not 0. gz is 0. This term is not 0 because uz is function of r. This is what we know, and there is nothing that makes us cancel this term. And you need to be careful here because, you know, while you're canceling a lot of terms, you might cancel something by mistake, so you need to be careful. Here uz is not function of theta, uz is not function of z, so the only terms left is negative dp by dz and this term. So we can rearrange the equation to have it d by dr of r duz by dr equals r over mu times dp by dz. I just moved it to the other side and multiplied by r over mu. And then we can integrate it once. So we have r duz by dr is the integration of this. So we add 1 to the power and divide by the new power and add this c. Of course, this dp by dz is constant. So we deal with it as a constant. It's not like a partial differential equation now. Now we can divide the equation by r and integrate it one more time. So if you divide by r, it's r over 2 mu dp by dz plus c1 over r. If you integrate it again, it's going to be r squared over 4 mu, and this c1 over r will be c1 ln r, and then we'll have c2. So this is the profile that we have. Now we can apply the boundary conditions that we have to solve this equation. For the boundary conditions, we have two conditions. The first is when r equals 0, du by dz is duz by dr is 0. So we can apply it here. If we apply here r equals 0 and du by dz is 0, this r equals 0, so c1 is 0. Okay, and now we can so this term is cancelled now. Now we can apply the second boundary condition that u equals 0 when r equals r capital or uppercase r. So this is 0 and this is 0 as well. So we have here uppercase r square over 4 mu dp by dz plus c2. So c2 is negative this term. And now we can substitute with c2 here in this equation, and this is the velocity profile, which we can put it this way. It's 1 over 4 mu times dp by dz times r square minus uppercase r square. So this is the velocity profile we are interested in. And this is the first requirement. The second was the shear force. So the shear force is tau equals mu du by dz, du by dr. So du by dr is already here, so it's going to be r over 2 mu dp by dz plus c1 over, or c1 is 0. So it's going to be just this, which is, or the derivative of this equation, whatever you like to do, it's going to work. So it's going to be r over 2 times dp by dz. So if r is r capital, which is the pipe wall, then this is r capital over 2 times dp by dz. So these are the results that we got. So there are some interesting things you need to pay attention to now. The first is that from this equation, we know it's laminar flow. We see that the velocity profile is parabolic, which is r square, which is proportional to r power 2, which is what we know from before. We know that the velocity profile in laminar flow is parabolic profile. So this makes a lot of sense. For this equation, we see that the shear stress is has a linear dependence on the radius. So for r equals 0, the shear stress is 0, and for uppercase r is going to be maximum. Okay, so this makes a lot of sense because at the center line, it's very, very far from the center, so there is no effect of the walls or the shear stress of the wall. So this is the profiles. I also did like what I did in the previous examples. I plotted the profiles at different viscosities here. So this is the velocity versus the radius. So this is half the pipe. So this is starting from the center line all the way to the maximum radius. I took the radius as 10 centimeters. So I took this. This is the radius. And you see here, depending on the viscosity, we have this is the maximum viscosity and this is the minimum viscosity. So for the minimum viscosity, you'd see, of course, it makes a lot of sense that if the viscosity is low, then the velocity would be high. And as the viscosity decreases, you'd see that increases, the velocity will decrease. You'll also see here the same thing, that all the profiles will have a slope of the velocity with respect to radius is 0. So this is kind of perpendicular tangent here. And this is because there is another one below. So if you want to see the whole velocity profile, this is half the velocity profile. If you want to see the whole velocity profile, it's going to be a mirror image of this. So this is the profile that we are used to for laminar flow, and it makes a lot of sense. Okay. For the shear force, this is what I was just saying in the previous slide, that it's 0 at the center, and as the radius increases, the shear force will increase until it reaches the maximum value at r equals r capital. So this is all for this chapter, and by this we are done with what we will cover in chapter 9, and this is the end of the course. I hope it was useful. And as I told you before, there are some extra materials that I'm going to be recording and posting here for fluid mechanics related topics that that we don't cover here. And I already have these materials from before, so I posted after this video. Hopefully they will be of help for you. So I'll see you then, inshallah. Goodbye.